Welcome to the Blue Economy CRC webinar series for this year 2024. I'm Professor C.M. Wang, the Program Leader of Offshore Engineering and Technology at the Blue Economy CRC, as well as Professor in Structural Engineering in the University of Queensland. Firstly, on behalf of the Blue Economy CRC, I would like to begin by acknowledging the traditional custodians of the land on which we are hosting this seminar and pay our respects to their elders, past and present, and also I extend respect to the Aboriginal and Torres Strait Islander peoples, which may join us here today. The Blue Economy CRC was established with a 10-year life under the Australian government CRC program in July 2019. So we are now 5 years old. With over 44 participants from Australia and around the globe, the purpose of the Blue Economy CRC is to perform world-class collaborative industry-focused research and training that underpin the growth of the blue economy through increased offshore sustainable aquaculture and renewable energy production. Now, today's webinar is about the Blue Economy Symposium held at the OMAE 2024 conference in Singapore. The first Blue Economy Symposium was held at the OMAE 42nd International Conference on Ocean, Offshore and Arctic Engineering, which was held in Melbourne last year in 2023. Now, owing to its success, the symposium now has become a permanent feature in OMAE, and it now covers emerging technologies in the context of the blue economy with a focus on aquaculture and renewable energy applications. In this webinar, 3 presentations were selected to cover some of the aforementioned topics in the context of the blue economy. Now, there is a Q&A tab there. If there's any questions you have for the speakers, please do put your question through the Q&A tab. We will take all the questions towards the end of the webinar. That means after all the 3 presentations. So without further ado, I would like to introduce to you our first speaker, Per Arild Alland, who is a business development manager in DNV, Norway. His presentation title is Industrialization of Ocean Fish Farming Contributing to Boost Supply of Marine Proteins, Solutions and Challenges. So may I invite Per Arild to the microphone. Per, please.
Thank you, Professor Wang. Thank you very much for a kind introduction, and thanks for having me, contributing to this interesting and very fascinating topic. Let me share my screen with you folks to make sure that you are able to see my slides. Like that, I hope. I hope you can see my slide, my front slide now, everybody, just to make sure.
Yes, we can see it now, Per.
Okay, thank you. Yes. So as just mentioned, what I would like to focus on in this presentation is how the industrialization of the fish farming industry is rapidly progressing, and how this is able to contribute to the supply and demand, very dramatic supply and demand imbalance that we see in the fish food sector these days. Trying to highlight a few solutions for you and structure it from this perspective of what is going on in the northern part of Europe, and looking into a few challenges and solutions that we can see. Myself, I work in the classification society, DNV, with certification and assurance to ensure safety and security of these facilities. So with that, I'll change the screen and just to remind ourselves that this is what we have to relate to. Nice and fascinating rough sea. And we have this term seavolution that we would like also to put on the top of the agenda, and just to make sure that we understand each other, the so-called seavolution is on. It's a revolution going on when it comes to new and disruptive methods to perform fish farming. It happens in the ocean space at sea, where we see more and more opportunities to use the ocean space in new ways, among other things, to, of course, generate green energy, and also, as we're going to focus on today, the fish farming sector, where we grow marine protein from the so-called blue field. Indeed, we have a number of so-called forecasts where we are trying to predict the projections and development of various industries, and the one that parts of my presentation is based on is the so-called seafood forecast, Ocean Future 2050. That is possible to download on the web. It's just to Google it, and you could have it for free on our website. Okay, a bit more to the point. Some of the numbers that comes up in this so-called seafood forecast is most of them are based on projections of a future demand in the world's population for seafood. Partly based on also consumer preferences and how consumer preferences will develop over time, both when it comes to healthy food, sustainability, and accessibility of the smart proteins that we get from the sea. If we look a little bit into the numbers and the graphics that you can see on this slide, what is interesting is that we foresee an approximate consumption in 2050 of finfish from fish farming, not wild catch. Finfish from fish farming in the range of 23 million tons a year. We can see here that according to most people agree in this, that the finfish will actually grow faster than the mollusks and the crustaceans over time. And some of the important facts here are that if we view it from a perspective of what kind of methods and segments that will be able to supply products, we see that we still expect a significant growth in the sheltered fish farming, but then you see the onshore that I'm pointing on now will grow quite a lot, and also the offshore. In the big picture, these graphics may seem a little bit not significant when it comes to the offshore part, but we will see I will try to uncover some of the consequences a little bit better for you in the next slide that comes up. Something that we should bring along is that we foresee that in 2050, we will have in a range of 12% from onshore facilities, land-based, 12% of the consumption, and also last but not least, 7% from offshore, more inventive, exposed, high volume installations that needs to be operated. And the consequences of this is, of course, that to actually be able to meet the demand in 2050 for 23.2 million tons a year, if we assume, as we did, that 7% of these is supplied from offshore facilities, predicting approximately 5% loss, hopefully less than that, but in the worst case, 5% loss. We know that in Northern Europe, sheltered fish farming are struggling with significant loss. Sometimes we see losses of about 15 to 20%. The result will then actually be that in order to, if you look into these numbers, and in order to be able to reach this share of 7% of 23.2 millions, you need to put you actually need to put 6 fairly big offshore fish farming installation in operation each year. I tried to illustrate that with a fish farming installation that is fairly well known. The first one put in operation, it's called Ocean Farm 1, operated here in the middle part of Norway. 6 of these, and just to remind you, this is fairly big giants with in the range of able to supply about 6,000 tons of salmon each year. Now we're talking finfish, of course, also embrace all the other species, but this one is especially designed for salmon. So what I'm trying to raise is the awareness of future demand of seafood. And in order to meet this demand, a number of methods needs to be put to use, among other things, offshore fish farming, and the consequence is around 6 of these installations to be put in operation each year, which I think is fascinating. Also, when we look into various methods and approaches to do exposed fish farming or more offshore fish farming, what I would like to do is to show you this fairly crowded graphics, but I think it illustrates fairly well the process of fish farming and the flow, and what we need to relate to when it comes to operating these facilities. So if you start from the left, you have land-based smolt, usually. Then you have the transport of fish, live fish. There's a lot of transport of live fish, which I'm trying to highlight here. And we can see this development very clearly in the number of live fish carriers, which is a fairly advanced vessel to design and operate. Also, if you move further, you have traditional sheltered fish farming. You have the land-based grow-out facilities. And then you have, among other things, exposed offshore. And what we expect is, of course, that these two, the offshore arrow and the land-based arrow, will grow quite a lot in the future. And also an interesting feature here is that in order for the fish to be fit to meet the demanding environment, among other things in offshore facilities, we are putting to work this post-smolt, keeping the fish a bit longer in a boot camp to grow a bit bigger in order to be ready to put into sea. So this land-based grow-out facility we will see coming up, and also the offshore. The last one that I just want to highlight is the fish feed that is essential in order to make this happen. Fish feed is often representing in a range of 70%, 60-70% of the carbon footprint of the final fish farming product, and represents a significant cost in operation. So nice to have that as we move on. Emerging technologies that reflects very much what the process development that we just saw. We have the conventional that we should not forget. There is a rapidly evolving technology and industrialization in this segment as well. And then you have the exposed offshore, you have onshore, and you have what we call a semi-closed, a new partly closed technology that is put into water. We can look a little bit further into that a bit later. Ways to structure this and get a little bit overview of what is essential designing and operating these installations. We have chosen to focus on, split into three, focus on location, manning on board, and how it is actually operated and what kind of technology is involved as you operate these installations. So location, we have structured that into nearshore, exposed, and offshore. Manning, is it permanently manned or only daily manned, or is it remotely operated and unmanned? And then last but not least, the operation. And here we could make a long list, put down a few highlights for you. Remote operation, you have very often, you have land power, you have hydro generated electricity that are transferred through land cable. Sometimes you have hybrid concepts with battery operation. Some of them are gas fueled, and of course the autonomy and the control and instrumentation on board. Bring up a few examples for you that is either in operation or in the planning phase. So this one, SalMar's aquaculture, as you can see from the graphics, this is about 60 meter in diameter. No, sorry, 30 meter in diameter. Semi-closed tank. It is very near shore. It is unmanned, and that's it. So it operates on in sheltered, traditional sheltered location, but still new advanced technology is put to use to shelter the fish from parasites, for example. You can see here the top part of the water column is solid. Another example of where you have a near shore, it is actually daily manned. Nobody sleeps on board, are meant to, but usually remotely operated. It's powered by land. It's this new concept called the Fjordmax, with that is with this delta-shaped triple pen solution. It illustrates the sort of nearshore daily manned solution fairly well. Last one is offshore. It is permanently manned. It's hybrid concept, and it's this so-called smart fish farm that is meant to be operated as a regular oil and gas offshore installation. Just that you are increasing the complexity by putting live animals on board, of course. So that was the location, manning, and operation. Another way of viewing this is looking into what kind of technology or technological concepts that are put to use when you view these fish farms. So the traditional three split here is the open, semi-closed, and the closed, which is fairly well known to most people. The open net is a net pen. steel framework illustrated here by the Ocean Farm 1 that we just talked about initially. Secondly, an interesting concept that is emerging rapidly now is that the so-called semi-closed one, usually circular shaped with a grating at the bottom, but you have a solid container that is keeping parasites from the fish crowd at the top part of the water column. This one here is called Norlox Hydra. It's being built in Turkey as we speak. It is meant to be delivered in a few months. Capacity of 3,000 tons per year. Will be put in operation. First fish, I think the plan is at the end of 2024, start of 2025. Last one that I want to bring up in this slide is the closed solution, becoming more and more relevant as in different authorities are prohibiting open net pens. And of course, this one is a modular solution from called Hexacage, where you could move cylinders in and out. And the closed concept is, of course, that you can filter the waste water, and you can get pure water from deep down, and you have an absolute separation environmentally when it comes to external
Excuse me for interrupting.
environment.
Excuse me for interrupting, Per. We have about 1 minute left for you for your
Okay.
presentation.
No worries, no problem.
Yeah.
The last one is submerged. We see a lot of submerged operation now moving ahead. So that was number 4. So usually you have open, semi-closed, you have closed, and then you have different variations of submerged operation. This one illustrated by the aqua loop that is being developed these days. Some of the designs that is being planned and to be built in the future, maybe to highlight the Ocean Sovereign French initiative, will be steaming and moving, and then the Ocean Farm 2, the second generation of the yellow one. As just the last slide, and a point that I would like to make is that operating these different solutions, we need to focus on the essential functions that will have to be carried out on board. There is no point of building a very nice fish farming installation if you are not able to perform live fish transfer, if you're not able to efficiently perform dead fish collection, to crowd the fish as you transfer it, and to perform efficient cleaning and hygienic operation, to name a few. So this is, I think, one of the main messages that we need to bring along as we are taking part in this very interesting industrial development of, among other things, offshore fish farming technology. So that was my last slide. Thanks very much. Thanks very much, Professor Wang.
Yeah, thank you. So you can stop sharing screen. Per, thank you so much for that very, very insightful aspects of how to farm fish, especially offshore, and looking forward to an exciting future in this development in this area. So thank you so much, Per. So our next presentation will be 2 lovely ladies from the Plant and Food Research Institute of New Zealand. They are both senior scientists, so Louise Kreting and Susie Black. And their presentation is entitled Designing for the Animal, Reimagining Offshore Fish Structure. This is quite unique. So may I pass this microphone to Susie to take it through the presentation.
Thanks, Professor Wang. Thanks for the introduction. And I have my colleague, Dr. Louise Kreting, with me as well. She'll be taking over around halfway through. So we'll get underway. As Professor Wang said, this presentation is called Designing for the Animal, and looking at reimagining offshore fish structures. And of course, it's not just down to Louise and I. We've got a large team behind us as well, and quite a large project that we'll talk a little bit about. So fish-focused design, what do we mean by that? Well, we're a bunch of fish physiologists at heart, the team that started this project. So our focus is very much on the whole animal. And wanting to know what do the fish need to be at their best. So it's very much from the fish's perspective. And so the way we think about it is, rather than fitting an animal into a process like building a big structure and putting a fish in it and hoping it'll be happy, we've very much focused on the animal and built a system around the animal and hopefully have designed it in such a way that it's great for the fish. So from a fish's perspective, what might it not look like that would be great for the fish? Now, you've all seen these pictures. Per had them up just before as well. These are, hugely engineered structures, but they may not necessarily be great for the animal. And so we were very much looking through the fish's eyes and thinking, what do they need to be at their best? And this is the concept that we came up with a number of years ago. So ignoring the large vessel in the middle, we've got a fish enclosure structure, this big tube here that's submerged below the water. So getting below that high energy wave area down to around, say, 10 to 15 meters deep. And it's been made mobile by, and this is just a concept design here, and definitely not the real deal, a movable structure that's connected to the fish enclosure through an umbilical. But this vessel, if you like, contains the feeding mechanisms, all the monitoring devices, comms, etc. So we have our what we call the mover and the fish enclosure structure. And we were very much thinking about soft engineering solutions here. So rather than thinking about hugely engineered systems that are, huge steel structures that withstand the environment, we were very much thinking about soft engineered solutions that could work with the environment. So in thinking about it, we were thinking about it being, with mobile production being the Pacific way. So very much a New Zealand inspired design and concept, and very much designed around the needs of the fish. So the biological needs of the fish, thinking about how fast they swim, the species specific needs of the fish. And this idea of being mobile really plays to New Zealand's geographic and oceanographic strengths. We've got a very large exclusive economic zone, and it's a great way to be able to use it. Currently, you may know that the existing static aquaculture sites in New Zealand, they're very limited as they are around the globe. And so if there's a way to utilise more production area, then this may be an opportunity to do that. And we see a mobile system alleviating a number of issues. There's that social license issue around coastal occupation. Environmental footprint is obviously a huge issue around waste and benthic impact. And being able to have your fish in optimal conditions year round is a real bonus. You can imagine the opportunities and benefits for growth, health, welfare for your animals. And thinking about some resilience, and that's around climate change. So as sea temperatures warm or cool in certain situations, you can actually move your fish to wherever they need to be for their best growth and health. And it allows for species diversification. In New Zealand, we only grow one species in the sea, and that's not even a New Zealand native species, it's Chinook salmon. So it opens up some opportunity to be able to look at other species so we can diversify. So as I mentioned before, we're looking at these soft engineered solutions, and it's very much a flexible, a mobile and readily tunable system. So that's something that you can actually and potentially tune for as the fish grows. So if you need to change the flow that is going through the system as the fish grows, you can. So you're not, and being mobile, it means you're not limited to those site-specific environmental changes. You're not limited to the water quality where you're stuck in one site. And focusing again on designing for the needs of the fish, we're really looking at what and trying to understand what do the fish prefer and what is optimal for the fish, because they may be slightly different. It may be that I like to sit on the couch, but it may not be optimal for me. And the same with the fish. It's there may be a preference, but what's optimal for them, and there'll be a balance in there somewhere. We really do think that this type of system will produce high welfare, healthy and resilient fish with a mind for having a light environmental footprint. So the research program that this is happening under is called Reimagining Aquaculture. It's a 6-year program. It started back in October 2019, so we're 5 years in. And the objective was very much around taking seafood production beyond wild capture, beyond traditional static aquaculture into a new era of mobile production. And we've got a huge number of technological challenges, and here's the 3 key ones that we were looking at in this one. And that's developing a production system that's all about the fish, designing it for the fish and what they need. Designing an environmentally compliant system. So again, that soft engineering focus and utilizing hydrodynamic forces and not trying to design against them, but utilizing them for your advantage. And being able to be mobile so you can optimize conditions year round. And I must stress, this program is very much a proof of concept. It's not designed, it's not in scope to have a commercial product by the end of it, but definitely a proof of concept program. So I'm actually now going to hand over to Louise Creechting, who's going to take you through some other aspects of the program. So hopefully Louise
thanks, Susie,
and I'll jump out.
Thanks very much, and thanks very much for inviting us also to the to host for the in this webinar. I'm going to go more on like what are the key requirements, sort of the physical, the biology side of the well-being when we think about the fish-centric device or the fish-centric structure. So obviously the key one is temperature. And we know that you know, the surface waters are obviously sensitive to thermal variation, and we know around the world that when the fish are near the surface, that this has been creating issues, especially in coastal environments, more shallow areas, more areas that are quite calm, especially during the summertime, and that we're getting more heat waves around the area, around the world as well. So we need to sort of think about, well, you know, with this mobile production system, can we actually move fish to areas that are better for the temperature for them? So it's not just the depth, because there's a lot of, you know, there's now a lot of technology thinking about being able to drop a sea pen down to below, you know, 10, 15 meters. But we're also thinking geographically, can we actually move the fish from one area or one geographic area right through to another? So the solution we're sort of thinking here is designing the fully mobile system that can actually be moved both vertically and also horizontally. Susie, next. So some research that's been ongoing to understand the fish preference, because the temperature preference, because like Susie said, you know, we might all like to be on a couch, but it might not actually be optimal for us. So understanding the temperature preference, but also how this might be optimal for a fish. There's been some work been going on by a PhD student here at Selwyn, here in Auckland University. And this is just a small example of understanding the fish's physiology, looking at using the shuttle box method. So basically we've got a cooler system and a warmer system. And when the fish spends a long time in the cooler, it will actually start cooling down even further. And then when it gets too cold, the fish will move, or when it doesn't like it, it will move into the warmer. That side starts warming up until eventually you get it goes into an area where it's actually, you know, that's where it would like to be. So this work's been ongoing, and it's now already in publication if anybody's interested in further in this research. And then, of course, another key requirement or another aspect that we really need to consider is actually water motion in the environment. We know, I mean, the fish are living in this 3D environment. When we think about, you know, going offshore or out into the environment, you know, we've got waves that we need to contend with. We've got strong currents that we need to contend with. And there in the open ocean, especially when we think about these mobile production systems, we have to consider, you know, the where the wave climate is going to be the maximum, and it's going to potential, you know, there is potential for damage and for stress of the fish. So we need to tailor the hydrodynamic conditions to suit the species. And again, this could be where the mobile system comes in, that you can actually reduce or lower the system down out of, say, for example, a storm. You know, we can predict a storm is coming. We're starting to be able to do this in more accurate. So you could actually, you know, drop the system, or if you know, several days in advance, you could actually move the system out away from that particular area, if you know that that's going to be like where the eye of the storm is sort of passing through, for example. And we've just been doing some research on looking at you know, swimming of the fish at different flow speeds. And actually, this is a work by another PhD student, Wisdom. He was here doing some work at Plant and Food, but he's from Wageningen. And also this work has actually been published as well. So if anybody's interested in looking more at like this was for the salmon, looking at, like, you know, their flow preference and what they prefer and how well they're doing, then yeah, please have a look at some of his research that he's now it's in publication. So obviously, if we think about, if we have, you know, optimal temperature, if we have optimal water motion, another critical aspect obviously is the water quality. So we need to consider that specifically the dissolved oxygen, ensure that there's, you know, minimal physical damage to the animal as well. And basically, if you get all these, hopefully that's the whole point of this, you know, understanding from the fish's point of view, that if you get all these parameters correct, you know, you're going to get quite a happy, productive fish that grows well and is a healthy fish that, you know, so you're reducing the chances of mortality as well. So when we thought, you know, when the program has started and it's been, you know, there's a lot been going on, there's a big team that's working on this, and, you know, there's several aspects that we have to think when we start trying to design the actual structure underwater. The first one obviously is the material strength. We've got a lot of large predators in the environment. We have to think of the seals, the sharks. They're going to, you know, this kind of system, we need to really make sure that it's strong enough that can maintain them, but also obviously to ensure that the fish can't escape from it either. When it's mobile or when it's within the water column, we have to ensure that it maintains shape. There's a lot of research now going on, you know, especially for nets, the deformation of them, so that they can become deformed, and that actually reduces the area for the fish to be swimming in, and that can also create damage. So we have to consider that the structure itself maintains shape. Obviously, it maintains its buoyancy, so whether, you know, that it remains at a certain level, it's not continually moving up and down. We have to have it in an optimized flow environment, so understanding the flow dynamics in the environment, and also when it's mobile, you know, if you're pulling it along, what kind of speeds are you're pulling it in, and this will be dependent on the size of the fish as well. Another key aspect or criteria that we have to consider is the limited biofouling. Obviously, nets, there'll be a net at the front and the back, obviously a mesh, and biofouling is always going to be something high on that we need to consider when we're thinking about, you know, mobile aquaculture. Scalable, and when I say scalable, you know, we don't necessarily need to have really, really massive structures. We can have smaller structures depending on the size of the fish, depending on the fish species. So this is the other interesting aspect of this work, is also that it's, you know, you could design for the different types of species, and not one, you know, there's not one size that fits all kind of thing. We can tailor it to each individual species that you're interested in. And obviously the sustainability of the system. We want to obviously minimize the environmental footprint. So these are all these kind of areas that we've been looking at to, you know, the criteria for the fish-centric design. So what do these prototypes look like? Just quickly, we've got originally it started off, you know, looking at it in the pool. and towing along and making sure it remains inflated. We're now moving through to actually deploying them in the sea. So we've got our prototypes already going into the water and develop. And sort of these are the two things, what they sort of look like. We've got a lovely photo of the Nelson Tasman's site, during a nice calm flat day. But obviously the weather can get quite, changeable. You can get waves and that. So you can get quite a bit more, wave environment coming through for storm events. So yeah, we're already moving through from the laboratory and into the environment now with these. So just to sort of sum up the research we've been doing, it's a multidisciplinary approach to address the design challenges. It's not an easy area to consider or to work in, and especially when we're thinking about it specifically from the fisher's point of view rather than from the engineering point of view. So we're looking at a lot of different things to look at how to, for growing them, for transporting them, for harvesting the fish offshore, and obviously identifying the key requirements for the fish. And as we said, it's not, each fish species will be quite different. So we've been looking at a lot of snapper, but also, what about the salmon? So each, the well-being of that is species specific. And the ultimate end of this is that if we have happy, healthy fish, we're going to increase the production of them. So that's sort of where we're at with the project. And I think we've got one more slide. So this was all presented at the OMAE. There's a number of other papers that have also been presented. So if anybody's interested further on the research and from different area points of view. So we've been like oxygen and the internal oxygen inside, and also the SynTef have been doing work on the moorings, etc. If you're interested, we've got other papers already on this. So
yeah,
and
thank you very much, Louise and Susie, for sharing with us a very novel fish pen. This is
thanks very much.
Quite revolutionary, I must say. Okay, so let's move to the last presentation. The last presentation will be done by Professor Dong Nguyen. He is a professor in cybernetics in NTNU, Norwegian University of Science and Technology. So his topic of presentation is digital twin driven optimal design of connector stiffness for floating multi-modular structures and application for floating solar energy harvest. So without further ado, can I invite Dong to make his presentation? Dong, over to you.
Prof. Wang.
Yeah.
Yes, thank you, Prof. Wang. Can you hear and see me well?
Can hear you and see. Yes.
Yeah, thank you. Okay. Thank you, Prof. Wang. Hi, everyone. Thanks for inviting me to this webinar. As Prof. Wang has mentioned, my presentation is going to be a little bit more technical than the two previous presentations. And I really appreciate the three previous speakers, which has a very high level on both aquaculture and domain. So in my presentation, I will move towards the production of solar energy. We wanted to move further offshore. So the challenge is unique and a bit different from the floating solar infrastructure that is a little bit shelter and in inland. So this work has been done by my PhD student, Trina, and also my master student, Stian. Here is my presentation, and I go directly into a little bit of a brief introduction of floating infrastructure. You can have the floating structure to be used in the urban expansion to cope with the sea level rise and expansion of the population of the world. And as the two previous presentations, we have floating structure for aquaculture to secure the food sources for the human. the very emerging and very hot trending now is a floating structure for renewable energy. We have a floating wind, we have wave energy converter, and also floating solar. The final one was maybe has less attention. It can also cause some negative effect on the seabed, like extraction of minerals at the seafloor. So in my presentation, I will focus more on floating solar. So the idea is that we want to cover the very large area for solar energy production, and we want to move to the offshore, and there we have waves effect. And in order to mitigate this wave effect, the idea is that we partition the large area into a smaller area. In this concept, let's say we have divided the whole structure into 10 by 10 meter module, and then connect them together via the connector here. And this poses a challenge to this structure at the connectors here, where we have the fatigue, the loads, and the motion, the relative motion between the modules. So in order to cope with this, our research group proposed to have a so-called intelligent multi-modular structure. So why do we call it intelligent? It is, we would like to propose that the connector here can be able to change the stiffness, and so that we can change the dynamics of the whole structure. So in order to do that, we need to understand the dynamics of the structure by looking at the hydrodynamics and the structure aspects of the whole structure. We need to have the material that can actuate the stiffness or even the damper at the connector here. And then we need to have some kind of looking at the control theory to control the whole floating structure. However, in this presentation, I only looking at a little bit higher level on how do we choose the stiffness at this connector so that we can mitigate the wave load effect. So the objective of this presentation is we would like to propose an optimization algorithm to design the stiffness at the connector among the modules. In order to do that, we would like to propose a digital twin, a kind of an early phase digital twin or a simulator, and then to combine with one optimization method called Bayesian optimization. So to define a digital twin, this is the virtual copy of the physical asset. This physical asset is this multi-modular for solar energy production. And in this work, we consider this as an early phase digital twin. You know that the digital twin, it need to be going along with the physical assets for the whole life cycle, where the digital twin will we need to adjust to the physical asset if we have the real data and so on. But because this type of structure is still in research, it has not been much data gathered. So this is kind of an early phase digital twin. And if we look at the stiffness of the modules or the stiffness of the connectors, they can be either rigid or flexible. So this end up with in four possibilities: rigid module and flexible connector, rigid module and rigid connector, and so on. So in our work now, we consider the module is rigid and the connector is flexible. That means it can be it can change the characteristic. To develop the early phase digital twin, we first look at one module, very simple, by consider potential theory. For example, here is the underwater part of one module, where we use that to calculate this owner hydrodynamics coefficient like active mass, potential damping, excitation wave loads, and so on. And so each module will connect to 4 neighbors modules via connectors here. In this work, we consider the connector as a spring. And of course, we can also consider with additional like dampers and so on. And this is how we simulate the whole structure. Basically, we look at one module, simulate that one module, and then we look at the neighbor modules and also simulate that motion. And then we look at the derivative motion of the 2 modules, and then we apply the hook law for the connectors because it's just a string. Yeah, so then I will move into the Bayesian optimization method. This is a gradient-free global optimization method. The motivation behind choosing this Bayesian optimization is that we have a large structure with a lot of modules. Let's say it can be 10 by 10 or at least 100 modules. And it becomes very expensive to evaluate the performance of the whole structure. So by using this Bayesian optimization, the idea is that it will guide the search into a more feasible or more optimal region without spending too much effort on simulating any other region. Similar to all of the optimization, we need to define the cost function and with some constraint. The cost function in this work is we consider the relative motion between modules, and then we also consider the loads going through the connectors, and then we have the weighting so that we can choose which one we want to prioritize. So the main idea of Bayesian optimization has 2 parts. The first part is that we kind of evaluate the cost function at some random places. And then from this random cost function evaluation, the Bayesian will try to guide the next search so that we focus more on the area where it thinks that it's going to be a global optimal solution. The use case is this. This is an early concept that was, I think, proposed by Equinor and Aker Solution in Norway. So the idea is that each module will have the size of 12 by 12 meter, and it has 4 pontoon or it's a cylinder. It can also be a rectangular cylinder and so on. So the draft is around 1 meter and so on. So here for each module, the mass is around 10 ton. So on the right-hand side, you see that this is a result coming from the combined approach using digital twin plus Bayesian optimization. We see that so it is in the first row, the result for 3 by 1 configuration, if you can see from the left-hand side. So how it looks like in the lab. And in the first figure, the wave is quite short, and then we increase the length of the wave. You see that for the short waves, the stiffness it should be soft. The spring at the connector should be soft, and then when we increase the wavelength, then it should be harder, stiffer at the connector. A similar trend you can see from 2x2 configuration. To validate the approach, we compare with the experiment. So in this slide, we saw the result when we compare 3x1 configuration with the experiment in the lab, and the wait period is about 7 seconds. And at the red line here are the stiffness that we evaluate at the lab, and the blue line here is the result from the optimization. Yeah, so from the lab we see that the stiffness is around here, which is a little bit soft. But from the simulation result, we are able to simulate even stiffer connector, and we see that maybe we should choose here, which can be very stiff. For the verification, what we did is that we evaluate the cost function at very fine grid for the stiffness, and then we compare with what Bayesian optimization does. And we see that the Bayesian optimization evaluate a lot of points at where we think it should be the optimal solution. So to summarize my presentation, we have proposed a so-called combined approach to use both digital twin and one optimization method. And this approach seems to have a potential to mitigate the connector loads and the motion by finding the optimal solution. This optimization we propose using Bayesian optimization seems to be effective for determining the optimal connector stiffness, given that the cost function is very expensive to evaluate. For further work, these are just the 3 points, but we also look at a much bigger picture. Like we also had some master work to look at how we test the smart material to realize this connector that can change the stiffness. We also looked at collaborating with other PhD students to look at how we can enhance the digital twin fidelity, improve the simulation efficiency, and maybe we need to look at other optimization methods so that we can use for real time for control purposes. And that's it for my presentation.
Yeah.
Thank you
so much. Thank you so much, Don, for sharing with us your digital twin-driven optimal design of connector stiffness for floating multi-modular structure used for solar farm. Okay, because of time, I will ask each question for each speaker, but you got to answer in only 2 sentences. So I'll start off with you. You know, Ocean Farm 1 has been in operation for maybe 1 to 2 years now. Can you share with us what are the operational difficulties in an offshore site for their farm?
Yes, main operational difficulties are very much related to the regular marine operations that needs to be performed on any fish farm.
Yes.
It's routinely logistics of feed and supply, and of course attending and tending to the fish and maintaining the fish welfare on board when you perform fish crowding,
I see. Okay.
and fish transfer, these kind of things.
Right, because of the harsh environment. Yeah, thank you so much, Per, for sharing that point. For Luis and Susie, I find your mobile of fish pen very, very revolutionary. But I was wondering, what kind of fish are you farming? Because you're continuously submerged, so obviously it's not for salmon, because salmon needs air for the swim bladder. So what kind of fish are you thinking of farming in your
It's interesting you say that, Professor Wang. obviously in New Zealand, we're not farming Atlantic salmon here, we farm Chinook salmon over here, and
Ah,
they are
right.
actually one of our species that we are trying out in this prototype. On the 1st of July, I can proudly say we've finally got resource consent to be able to put fish in these prototypes,
Right.
to finally be able to try them with fish in them. So we'll see. The other species that we're looking at in this project is the New Zealand snapper.
Snapper.
So yeah, more temperate species, but yeah, we've done some work in the lab on Chinook, trying to replicate an experiment where we hold the Chinook salmon under the water to see if we get those welfare issues with them, with not being able to access the surface. And we haven't seen that with Chinook, and it's that they're on a different evolutionary line to Atlantics.
see.
There may be some issues there, but having a mobile structure that we can actually submerge, it means we can actually bring it to the surface as well. So
Yeah, that's right. Yeah.
there's opportunity there to have a mixed system where we can bring them to the surface if we need to.
Yeah, right. Because when you bring them to surface, for salmon, they need even to jump up from the water surface. They want that kind of atmosphere. But anyway, I presume all your fish will be trained to live in that kind of condition.
Yeah.
So I'm not sure whether you're fish centric. But anyway, good luck to your project.
Thank
Finally,
you.
to Dong. Dong, for your your multi-modular structure, how do you handle very, very large waves during storm? Are you going to submerge your entire floating solar farm?
Yes, I think this is a good question. Yeah, I agree. So to design this structure in ultimate state, it's going to be in. I think it's my short answer is still in the research. And I think maybe this is also some question to DNV also, that how do you approve this kind of structure? And that's the same story, that we need to do a lot of study on ultimate strength, and also even with the failure of the actuator of the control, then how can you also guarantee that still survive in the storm, for example?
Thanks, Dong. All the
Yes.
best to your research. So with
Thank
that
you.
note, I think we have to end our webinar, because it's so enjoyable to listen to people and they are so enthusiastic. So I'm so sorry that if we could not pose your questions to the speakers. So I just want to remind that that the recording of this webinar will be available a few days later, and it'll be posted on the Blue Economy CRC website. Please, we'll let you know, and you can go ahead and download and view it, or use it for your teaching purposes or for your promotion and so on. So please check out the CRC event page for any upcoming webinars and events. With that, I would like to wish everyone a very good night, or very good morning, or good afternoon, and may you have a good day. Thank you so much for joining us.
Thank you.
See you
Thank
again
you.
next time.
Thanks, everyone.
Thanks
Bye-bye.
very
Thank you.
much.
See you.
Bye.
See you again.
Bye bye.